All right, let's dive into a cosmic detective story. We're on the hunt for an invisible, unbelievably powerful force that literally holds our entire world together. Seriously, without this thing, you, me, this planet, everything would just instantly disintegrate. So let's start the investigation. And here's the central mystery, the big question. Deep inside every atom, you've got the nucleus, and it's packed, just crammed full of positively charged protons. Now, anyone who's played with magnets knows that like charges repel each other. So these protons should be shoving each other apart with an incredible force. So why doesn't the nucleus just explode? What in the universe is holding it together? You know, if you think about the nucleus like a crime scene, the fundamental laws of electricity seem to be completely broken. It just shouldn't work. We have this impossibly dense core of positive charge that, by all rights, has no business existing. It's a paradox at the very heart of all matter. And let's be really clear about the scale of this problem. The electromagnetic repulsion between two little protons stuck in a nucleus is, well, it's colossal. It is astronomically stronger than the force of gravity between them. So to solve this puzzle, we need a suspect. We need to find a force that's even more powerful, something totally new to physics. And that leads us directly to our prime suspect, who also happens to be the hero of our story, the strong nuclear force. This is the interaction that binds protons and neutrons together. And as you can guess from the name, it is hands down the most powerful force we know of in the entire universe. So, how does it overpower that relentless electrical push, the Coulomb force? Well, this slide basically gives you the tale of the tape. On one hand, the nuclear force is immensely, overwhelmingly strong. But, and this is a huge but, it only works over an incredibly short distance. The Coulomb force, while weaker up close, stretches on forever. So the nuclear force is like a heavyweight champion, but it can only fight inside its own tiny little boxing ring. And how tiny is that ring? Just 1 femtometer. A femtometer, or a Fermi, is a millionth of a billionth of a meter. It's a scale that's almost impossible to imagine. The best analogy is probably cosmic Velcro. It's got an unbreakable grip when two particles are basically touching. But pull them even a tiny, tiny bit apart, and that force just vanishes. It's gone. So we've met our force, but here's the thing. It doesn't play by the rules we're used to from things like gravity or magnetism. It has a very quirky, almost counterintuitive personality. To really get a handle on it, we need to build a profile of all its bizarre behaviors. First up is a feature called saturation. You see, unlike gravity, which tries to pull on every single thing in the universe, the nuclear force gets satisfied, or saturated, very quickly. A proton, or a neutron, which physicists just call a nucleon, only really interacts with its closest neighbors. It doesn't care about the other particles on the far side of the nucleus. And that's why the density of all atomic nuclei, from helium all the way to uranium, is pretty much constant. And then there's this wild twist. If you try to get them too close, this incredibly attractive force suddenly flips and becomes powerfully repulsive. Think of it like personal space for particles. The force is great at pulling nucleons together, but it has this repulsive core that prevents them from ever squishing into each other. It's what keeps the nucleus from collapsing in on itself. Okay, now this is a huge clue in our detective story. The force is intensely picky about something called spin. Let's take the simplest pair you can imagine, 1 proton and 1 neutron. If their spins are aligned, both pointing in the same direction, they can bind together and form a nucleus. But if their spins are opposite, nope, no binding. The force just won't work. This spin dependence is a critical piece of its identity. And that simple proton-neutron pair, it's called a deuteron, and it is the smoking gun in our entire investigation. Because it's the simplest possible nucleus with more than 1 particle, it's our best window into how this force really operates. By studying this one simple structure, we can uncover the force's deepest secrets. So what do you think it looks like? I mean, you'd probably guess it's a perfect little sphere, right? Just 2 tiny balls stuck together. But is that really what the evidence tells us? What is the actual shape of a deuteron?
Well, the evidence is pretty surprising. It turns out, yeah, the deuteron is about 96% spherical, pretty much what we'd expect. But there's this small but very real 4% of the time where it's actually elongated, stretched out into a shape kind of like a football. Now, that's not a mistake or a measurement error. That's a critical clue.
And here's why that's so important. A simple force that just pulls directly between the centers of the 2 particles could never create that elongated shape. That 4% is undeniable proof that there's a more complex, directional part to the nuclear force, what physicists call a tensor force. It's not just a simple pull, it's a pull that has a preferred direction, and it's what stretches the nucleus out. So we know what the force does, and we know some of its weird rules, but we still don't know how it does it. How does the force actually work? For that, we have to turn to the final piece of our puzzle, a brilliant Nobel Prize-winning theory from a physicist named Hideki Yukawa.
Yukawa started with one of the deepest, most fundamental questions in all of physics. How do forces even work? I mean, how can two protons, even if they're right next to each other, feel a force across the empty space between them? He came up with a radical idea.
He proposed that the nucleons are playing a kind of quantum catch, tossing a special messenger particle back and forth. Now here's the genius part. Using the known range of the force, that 1 femtometer we talked about, he was actually able to calculate how heavy this messenger particle must be. His theory predicted a particle with a mass of about 140 mega-electron volts. And then, years later, wouldn't you know it, experiments discovered a particle with that exact mass, the pion. It was an incredible moment. Yukawa had solved the case, predicting a real particle just from pure theory. And this whole messenger particle idea, the exchange model, beautifully explains the force's weird personality. That main attractive grip, that's carried by those relatively light pions. But that short-range repulsive core we mentioned, well, that happens when they exchange much heavier particles, like rho and omega mesons. It's like having different messengers for different jobs. So, there you have it. The strong nuclear force is the universe's ultimate superglue. It's powerful, it's short-tempered, and it's quirky, but it's what makes all the matter we know and love possible. It holds the nucleus together with just incredible strength. Which of course leaves us with one final, very provocative thought. If this is the force holding things together, what would it take to overcome it and tear them apart? The answer to that question, well, that's where you unlock the power of the atom itself.